Okay, let's start 4.5 exponential and logarithmic equations. So you might be happy about this. You can use a calculator in this section, also on the exam, when not asked for an exact solution. So we'll be actually doing problems. Exact solution doesn't give us much information usually. So we usually want an approximate solution, and that's the reason a calculator is used. So these are the properties of logarithms we're going to be using to solve equations. So these restrictions are going to be an important part later on. So we're going to be looking at log to the base a. So it's not surprising that a has to be greater than 0 but not equal to 1. That's the normal restriction on a logarithm, the base of a logarithm. But x and y also have to be greater than 0. Why? Because the domain of a logarithm requires inputs greater than 0. So here's the first property we will use again and again and again. So recalling, if x is greater than 0 and y is greater than 0, then if x equals to y is equivalent to, which is the same as, the log to the base a of x is equal to log to the base a of y. And log, we also will use this, a raised to the exponent, so that's an exponent right there. So a raised to the log to the base a of x is equal to x. And another one, this is actually by definition, log to the base a of x is equal to b if and only if x is equal to a to the b. So this is by definition, and it's not hard to use this definition to derive this property. So let's use the first example. Let's solve a logarithmic equation, or an equation that we will use logs in the solution. So this is example 1. So I have 7 to the x, 7 to the power of x is equal to 12. And we're just going to assume that all of our x values are in the proper domain so that this makes sense. So what I'm going to do is I'm literally going to, if this is true, then what I'm going to do to solve it is, I say here in the instructions we want to use the natural log. But I also note that any base logarithm can be used, so if you're using a calculator, you have two choices, the natural log or the log to the base 10. So that's taking the natural log to both sides. So if I have an equality, then if I take the log to both sides, the equality holds. But I have a property of logs that say if I have log to the base a of x to the r, that's equal to r times log to the base a of x. So we're going to use that right here to bring the x down in front. Bring the x down in front is what we're going to do. So that's going to give me x times log to the base 7 is equal to natural log of 12. So here is my unknown. It's no longer in the exponent. That's perfect. And just recall that log, the natural log of 7, is a non-zero number. The natural log of 12 is a non-zero number. So it's this one that really matters. I can divide both sides by the natural log of 7. So that's going to give me x is equal to the natural log of 12 divided by the natural log of 7. So let's find out the approximate value of that. So this right here, the natural log of 12 divided by the natural log of 7, that is exact. But it doesn't give us much information. I have no idea where to locate it on the number line. So to find out where it is on the number line, let's solve it. So let's do log to the base 12 divided by the natural log to the base 7. And I get an approximative answer. The book is rounding off 3 places past the decimal, so that's 1.277. So I get 1.277. So I want to go back to the calculator. I just want to show you that it doesn't really matter which log we were to use. If I had chosen to use log to the base 10 of 12 divided by log to the base 10 of 7, I'm going to get the exact same answer. So let's go on to example 3. So example 3, it looks much harder than it really is. But we want to solve 3. And look up here, my exponent is a polynomial. It's 2x minus 1. And that's equal to 0.4 raised to the power of another polynomial, but this time it's x plus 2. So in this case, you can literally use any logarithm you want. You can use ln, the natural log, or the log to the base 10. It doesn't matter. So let's just use ln, and I'm going to take the natural log. Remember, ln means natural log. I'm going to take the natural log of both sides. Let me erase this and write it what it should be. So that's log to the 3 to the power of 2x minus 1. And this is going to be the log of 0.4 raised to x plus 2. So that implies that here's my exponent, and here's my exponent. So that implies 2x minus 1, it is minus, right? Yeah. Is equal to, sorry, not equal to, times there's my equal to x plus 2 So here I'm going to do something that the book does not do, but I think it makes it easier. So I'm going to let b equal the natural log of 3. And I'm going to let c equal to the natural log of 0.4. And I'm going to rewrite this using those terms. So I have 2x minus 1. The natural log of 3 is b. I just chose those values. I can't use x clearly, but I could choose r or s, but I chose b and c. Is equal to x plus 2 over c. And it's going to be easier at the end. I'm going to go back and re-substitute back in. But here I'm just going to use distribution. So b times 2x is 2bx. And b times minus 1 is minus b. And that's equal to c times x. So that's cx plus 2c. So what I want is all of my terms with x on one side and all of my other terms on the other. So that's going to give me 2bx minus cx, since I moved the cx to the other side. Now I'm going to move the minus b to the right hand side, so I get 2c plus b. So now I want to use the pull out the greatest common factor, which is using distribution. So this gives me x times 2b minus c is equal to 2c plus b. And now all I have to do is divide both sides through by 2b minus c. And 2b minus c. So I get x is equal to 2c plus b over 2b minus c. But now is the time to go back in and replace my variables with what they are. So x is equal to 2 times the natural log of 0.4 plus the natural log of 3 divided by 2 times the natural log of 3 minus the natural log of 4. So let's calculate what that is. That's the exact answer. So let's use the calculator to get an approximation of this. So let's bring up the calculator, clear it. It'll be easier if I just move this over. Can I make it bigger? Well, it doesn't make the buttons bigger. That's fine. Let's clear it out. So I'm going to go, since this is a division, is the primary mathematical operator, I'm going to put the numerator in parentheses. So I get 2 times the natural log of 0.4 plus the natural log of 3 in parentheses divided by, and again in parentheses, 2 times the natural log of 3 minus the natural log of 0.4. And I hit equal, and I get minus 2.36. So this is approximately equal to minus 0.236. So again, this is the exact solution, but it really doesn't tell you much, right? Where is this located on the number line? No idea. But when I use the calculator, I now know that it's actually negative, and on the number line, it's less than 0, but greater than minus 1. Oh, so that's actually example. There's a typo. That's okay. We can live with it. This should actually be example 2. I have 2 example 3s. That's okay. We can live with that. So example 3 has 2 parts. It's 3a and 3b. So let's do them. So here the choice of log is pretty set. We're asked to choose e raised to the power of x squared is equal to 200. So that e is Euler's e. So that tells me I really would be doing myself a disservice if I did anything other than take the natural log of both sides. I don't have to put parentheses there. And when I do, it's just to kind of remind you that the value in parentheses is the input to the function. Now I'm going to simplify the left-hand side because this is the exponent here. I'm going to use that exponent rule. So this exponent right here, which is all of this right here, comes out and goes to the front as a factor. So that's going to be my next step. So that's going to give me x squared times the natural log of e is equal to the natural log of 200. Now the natural log of 200 is just some number, and I don't know it. So the natural log of e is the same as, remember, ln is just another way of saying log to the base e. So ln of e is log to the base e of e, and that's always 1. So this is just 1. So that gives me x squared is equal to the natural log of 200. So now I just take the square root of both sides, and I get x is equal to plus or minus the square root of 200. So our solution set, our exact solution set, is minus the square root of 200 and the square root of 200. But let's go ahead and find out what the square root of 200 is. Sorry, that's supposed to be the ln of 200. Taking the square root of the ln of 200. ln of 200. So let's find out what that is using the calculator. So again, you'll look at your square root, ln 200, and I get, so that's going to be equal to plus 2.302 or minus 2.302. So the approximation is that x, the solution set, they don't do the set notation here. The book just will simply say the solution set, and the reason I'm doing this is because this is going to be minus 2.302 or plus 2.302, and this really is not true. This is the solution set of approximate values. This is the real solution set right there. But in my math lab, I have a feeling this is what they want you to enter, is that right there. So let's do number B. So here we're going to use a property of exponents. So this is 3b. And remember, a to the x times b, sorry, not b, times a. The bases have to be the same. A to the 2x is equal to a to the x plus 2x, which is equal to a to the 3x. In other words, this property follows from a raised to the power m times a raised to the power n is equal to a raised to the m plus n. And I'm going to be using something very similar to this right here to solve b. So we have e to the 2x plus 1 times e to the minus 4x is equal to 3 times e. So I'm going to, the base here is e, so I'm going to use this property. So this is the same as e raised to the 2x plus 1 minus 4x, and that's equal to 3 times e. So now I'm going to simplify the exponent up here. So 2x minus 4x is minus 2x And then when you add 1 to it, I get minus 2x plus 1. And that's equal to 3e. So again, the key here is my base is e. So I'm going to take the natural log of e to the minus 2x plus 1. And then I'm going to take the natural log of 3 times e. And we'll use some properties here to simplify the bottoming. Remember, another property that we have is log to the a times b is equal to the log a plus log b. And that's true to the log of any base. And we'll use that here. So the log of e to the minus 2x plus 1 just gives me minus 2x plus 1. And this is the same as the natural log of 3 plus the natural log of e. So the natural log of e is 1, so I have minus 2x plus 1 is equal to the natural log of 3 plus 1. So I'm subtract 1 from both sides. In other words, these vanish when I subtract 1 from both sides. And we get minus 2x is equal to the natural log of 3. So x is equal to the natural log of 3 divided by minus 2. So we'll figure out what that is. So the natural log of 3 divided by minus 2 is minus 5.49. It's approximately equal to, what was it again? Minus 0.549. So let's check and see. Yeah. Okay. Nope, not that. Let's go back to here. So here's going to be an example where we use the substitution method. Here's the hint we will have to take here. So this is example 4, and I have e. So again, we're going to be using the natural log when it gets down to it, times 4 times e to the x plus 3 is equal to 0. I don't think we actually, well, we'll see. So the hint says let u equal to e to the x. So that means u squared is equal to e to the x squared, which is the same as e to the 2x. So e to the 2x is u squared minus 4, and e to the x is u, plus 3 is equal to 0. So we want to factor this. So this factors into u minus 3 times u minus 1 is equal to 0. So now we just solve this. So that implies u minus 3 is equal to 0, or u minus 1 is equal to 0. That implies u is equal to 3, or u is equal to 1. So with that in mind, let's substitute u. U is e to the x. So e to the x is equal to 3, or e to the x is equal to 1. So let's concentrate on this one right now. We're going to solve both of them clearly, but I want you to think for just a second about this one. What number, e raised to what number, is equal to 1? And I hope if you think about it, the clear answer is that x is equal to 0, because we have the zero exponent theorem that says if b is not equal to 0, then b to the 0th power is equal to 1. So we're going to use another technique to solve e to the x is equal to 3, and it's the exact same technique that we've used before. If e to the x is equal to 3, then the natural log of e to the x is equal to the natural log of 3. But if the natural log of e to the x is equal to the natural log of 3, that implies x is equal to the natural log of 3. So that's the exact answer, and the approximate answer is, actually, it says give an exact value. The instructions say give an exact value. So our solution set is the natural log of 3 and 0. So x is either one of those two values. So again, now we're going to solve either of these two equations, and we're going to give exact values. So solving logarithmic equations isn't too bad, but you basically just have to use all of the properties of a logarithm to get to it. So we have 7 times the natural log of x is equal to 28. So I'm going to divide both sides through by 7, because this is 7 times the natural log of x. So that implies the natural log of x is equal to 28 divided by 7, which implies the natural log of x is equal to 4. So remember, how do you solve this? By definition, if the natural log, if you want to write the natural log is log to the base e of x is equal to 4, that implies e to the 4th power is equal to x. So e to the 4th power is equal to x. So literally the solution to this follows literally by definition. But there's another way you can also do it. If you have ln of x is equal to 4, so here's another property you can use. If a is equal to b, then for any real number c, c to the a is equal to c to the b. And I guess here we should say if c is not equal to 0, it's still true if c is equal to 0, but when you raise 0 to a power, you lose all information. You don't get anything useful. So using that property, if I wanted to solve it this way, and the reason I'm telling you this is I often solved it this way, we raise both sides. We take e and raise e to both sides. So e to the ln of x is equal to x by a previous property. So x is equal to e to the fourth. So that's actually, this is by definition, if you recall the very first thing when I was talking about those properties. This follows, this answer right here follows by definition. But the property I used right here is a property that follows by the definition, and I can use either of the two. So that's 5a. Let's look at 5b. So consider 5b. So we have log the base 2 of x cubed minus 19 is equal to 3. So this implies, by definition, that 2 raised to the third power is equal to this. So by definition, this means 2 raised to the third power is equal to x cubed minus 19. That's what that means. Again, if log to the base a of x is equal to y, then that implies a to the y is equal to x. And here our base is 2, and 3 stands in for my y, and the polynomial x cubed minus 19 stands in for my x. So now I can go ahead and simplify this and solve it. So 2 cubed is 8 is equal to x cubed minus 19. So I'm going to put 19 on the other side. That's going to give me 19 plus 8 is equal to x cubed. So that's 27 is equal to x cubed. But 27 is equal to 3 cubed. So 3 is equal to x. If you want to take the cube root of 27 and take the cube root of both sides, you'll still get the same thing, because how do we solve the cube root? We use the property the nth root of b to the n is equal to b. And either way you do it, however you get x is equal to 3, you're good to go. Okay, so now we're on several examples. None of them are really difficult. But again, we are using the logarithmic properties to solve these. So here we want exact values as well. So here we're going to use a property. So the first thing we need to do, where is my thing? Okay, is we have to be careful about our domain, because here we have two possibilities. The log of a number is only defined if that number is greater than 0. So we need x plus 6 to be greater than 0 and x plus 2 to be greater than 0. So the solution to x plus 6 greater than 0 is x has to be greater than minus 6, and x has to be greater than minus 2. I said minus 2 and wrote minus 6. So if x is greater than minus 6, that's this set right here. The and indicates we're going to take the intersection. And if x is greater than minus 2, that's this set right here. So this is just a quick review. So let's draw my number line. I'm going to draw two of them. So I'm going to say right here that this is minus 6. And I'm going to say this is minus 2. So this is going to be minus 6. Oh, I don't need it that big. And this is going to be minus 2. So what I do is, if you recall, for x greater than minus 6, that's all of that area. And for x greater than 2, that's all of this area. And since I'm taking the intersection of both sets, it's the area where both the upper number line and the lower number line are shaded in with my red. So that is x. Maybe that's too dim for you to see. So that means x has to be in the set minus 2 infinity. So when we solve this equation right here, if I get any value of x less than or equal to minus 2, it has to be rejected. The other property we're going to be using to solve this is the property of log A minus log B is the same as log A divided by B. And here I'm being really lazy. When I say log here, it's log to the base whatever. So I don't write it to the base because I'm tired to. So we're going to use that property. So let's go. This is number 6. So I have log. And this is actually log to the base 10 by definition of x plus 6 minus log to the base 10 of x plus 2 is equal to log of x. Wow. Here's log of x. I've got to add one other thing. So we also need x to be greater than 0. I forgot about the other side. So let's draw one more line. And draw a 0 right here. You already see what's happening. This is 0. So literally, I need x to be greater than or equal to 0. Because that is the overlying, that's the one that basically rules them all. So I have to take yet the intersection of one other set here just to be complete. And the intersection of these three sets is just 0 to infinity. So my x value has to be greater than 0. Now if I had something else on the other side other than the log of x, then things would be different, but that's what I have. So let's transform this equation right here. So this is the same as log of x plus 6 divided by x plus 2 is equal to log x. So again, we use if log b is equal to log c, because these are one-to-one functions, that implies b is equal to c. That's what it implies. So this implies x plus 6 divided by x plus 2 is equal to x. So this is the equation that we have to solve. And you're going to see it's going to be a quadratic, right? And we're going to solve it by multiplying, clearing the denominators by multiplying both sides by x plus 2. When I multiply this side by x plus 2, I am left with x plus 6. When I multiply the other side by x plus 2, I have x times x plus 2. So this gives me x plus 6 is equal to x squared plus 2x. I'm going to move all of these terms to the other side. 0 is equal to x squared plus 2x minus x minus 6. So 0 is equal to x squared plus x minus 6. And we're going to factor this, and we can indeed factor it. Hopefully you're getting good at factoring and you can do this in your head. This is x plus 3 times x minus 2. So this implies x plus 3 is equal to 0, or x minus 2 is equal to 0. But this implies x is equal to minus 3, and this implies x is equal to 2. But over here, our solution has to be greater than 0. So x minus 3 is rejected as a solution, and our solution set contains only one number, and that is 2. That is our solution set. So we got to be careful. Now you see with the whole introduction of the fact that our answers have to be in the domain of the function. We can't put something in this is what I need to do right here. Well, I'll do it that way if I have to. And here I'm reminding you of what I just talked about. So the domain of the logarithm is all positive numbers. So everything has to be greater than 0. So let's look at our next problem. Okay. This one's going to be interesting, so pay attention to this. So this is give exact values. That's fine. So I have log to the base 2 of 3x minus 7 times x minus 4 is equal to 3. Before we even begin to solve, we have to find values of x for which this product is positive. So that's what we're going to do first. We want to find values of x for which 3x minus 7 and x minus 4 is greater than 0. So there's two ways that can happen. 3x minus 7 is greater than 0 and x minus 4 is greater than 0. Or 3x minus 7 is less than 0 and x minus 4 is less than 0. So let's just solve the following equations, and then I'll show you how I do it. You can do it. If you have another way to do it, that's fine. So we're just going to solve the inequality 3x minus 7 is greater than 0. And that's going to give me x is greater than 7/3. And then I'm going to solve the inequality x minus 4 is greater than 0. and that gives me x is greater than 4. So what I'm going to do is I'm going to draw two number lines again. And I'm going to arbitrarily mark two places. One of these places is going to be 4, and 7 divided by 3 is less than 4. And get another color here. So let's look at x greater than 4. So this factor is positive if it's greater than 4 and negative if it's less than 4. We don't include 4. You can remind yourself by putting that there. Up here, the 7/3, if x is greater than 7/3, then 3x minus 7 is positive. And we don't include that value. And negative here. So what that means is the product of the two is going to be positive if x is less than 7/3 or if x is greater than 4. So this area right here, I have one factor positive and the other factor negative. A positive times a negative is a negative. So I need the area where they're both negative or both positive. So this is going to be our domain. So we can write our domain, possible answers, possible values, require x to be in minus infinity to 7/3, not including 7/3, or we take the union 4 to infinity. Okay, so now we're ready to work on this equation right here. So I'll copy it down again, and we'll come down and work on it down here, and we will move up to the top. So the first thing we did was find the possible domain values for our answer. So I had log to the base 2 of 3x minus 7 times x minus 4 is equal to 3. So again, remember, log to the base a of w is equal to b if and only if a raised to the power of b is equal to w. So this is going to be my w, and a is my base 2 and 3 is b. So this literally implies 2 to the third power is equal to 3x minus 7 times x minus 4. Well, 2 to the third power is 8. So this is going to be another quadratic equation. You should always try to factor these if you can. Factoring is usually easier than whipping out the quadratic equation. So I'm going to multiply out the right-hand side. This is 3x squared minus 12x minus 7x plus 28. So that's going to give me 0 is equal to 3x squared minus 12x minus 7x is minus 19x plus 28. I have to subtract the 8 that I just brought over. So I have 0 is equal to 3x squared minus 19x plus 20. So let's see if we can factor that. So just a little review on factoring. It never hurts, does it? So this has to be 3x in x. And let's try, since this is going to be a minus 19, and this is a positive, both of these have to be negative factors. So I'm going to try that. Minus 5 times minus 4 gives me 20. 3x times x gives me 3x squared. Now multiplying down this way, that gives me minus 15x minus 4x. So that gives me 19x. So that's the information I need. And remember again, if you got all the information, make sure you extract the right factorization by doing this kitty corner thing right here. So x is equal to 3x minus 4. Now I realize some of you factor differently. That's fine. You can factor any way you want. As long as you get the right answer, I don't care. And that's equal to 0. So that implies 3x minus 4 is equal to 0, or x minus 5 is equal to 0. So this implies x is equal to 4/3, and this implies x is equal to 5. So those are my two possible answers. If we go up here, it turns out that x has to be, so x equal to 5 clearly is in this side because x is greater than 4. And 4/3 is less than 7/3 because the denominator is the same and the numerator 4 is less than the numerator 7. So both of my answers work. So my solution set has both of them, 4/3 and 5. And one last problem. This is a good one. So again, this is number 8. So I have log of 3x plus 2 plus log of x minus 1 is equal to 1. So in this case, we have to have both 3x plus 2 greater than 0 and x minus 1 greater than 0. So this implies x is greater than minus 2/3, and this implies x is greater than 1. So both of these conditions have to hold, so that means our solution set is in the set of 1 infinity, because x has to be greater than 1 and minus 2/3. So anything greater than 1 is also greater than minus 2/3, but not the other way around. So x has to be greater than 1. So we're going to use the same procedure before. So we're going to use the rule log of x plus log of y is equal to log of xy provided x is greater than 0 and y is greater than 0. So that's the property we're going to use. And now that I've written the property, I want to erase it because it's in my way. But you all can write it down really fast. It's a property, I think, 2 lectures ago. So that's the same as, almost like before, 3x plus 2 times x minus 1 is equal to 1. So the easy way to take care of this is I got a log of something is equal to 1. So again, the base here, the unspoken base, is 10. So this implies 10 to the first power is equal to this right here. So that gives us 10, and let's multiply this out. 3x squared minus 3x plus 2x minus 2. Simplifying, this is 3x squared minus x minus 2. So I'm going to take the 10 to the other side. So it gives me 3x squared minus x minus 12 is equal to 0. So you can try to factor that. And it turns out that this is prime. It doesn't have a factorization. But we can still solve it. We can solve the equation by using the quadratic equation. So remember, we have ax squared plus bx plus c is equal to 0. So my a value is equal to 3. My b value is equal to minus 1. And my c value is equal to minus 12. So using the quadratic equation, I have, and just so you'll recall, quadratic equation states if this is true, then x is equal to minus b plus or minus the square root of b squared minus 4ac, all of it over 2a. So x is equal to, using the quadratic equation, so you all should try to factor that. And quickly you'll see that there is no factorization, so it's prime. So you have to use the quadratic equation. So x is equal to minus b, and b is minus 1, plus or minus the square root of b squared. So b is minus 1 squared minus 4 times a, which is 3, times c, which is minus 12. All of this is going to be divided by 2 times a, which is 3. So that's going to give me, after simplification, minus a minus 1 is 1, plus or minus the square root of 1 plus 144. That's what you get. Minus 4 times 3 is minus 12, and minus 12 times minus 12 is plus 144 over 6. So here you have to find out with the calculator what these answers are. And approximately, if I take the positive root first, I'm going to get x is about equal to 2.17. That's 1 plus the square root of 145 over 6. Or x is approximately equal to minus 1.84. Again, using the calculator for this. So going up here, what did we need our values for x to be? X had to be greater than 1. So my only solution is this solution right here. That's the only one that's greater than 1. And that corresponds to 1 plus the square root. 1 plus 144 is 145 divided by 6. So the exact solution is 1. I don't know if it asks for the exact solution or not. I forget. 145 over 6. And that is it. So that's an awful lot. Sorry, the lecture just takes a while. Notice when I do this, I do all of the problems. I don't skip any of them. And of course, you all have the option of watching these videos, watching the My Math Lab made videos, reading the book, or any combination of the above.